In this video, we are going to be talking about diffusion and effusion, which is part of our learning objective for describing the relationship between molecular velocities, kinetic energy, and the molar mass of a gas. Let's start off by defining diffusion and effusion. These words do sound very similar, but they do talk about different concepts that are related, but still different concepts. And so diffusion is the process in which a gas spreads out evenly from an area of high concentration to low concentration. And heavier particles are going to diffuse more slowly. If you are talking about a gas that's escaping through a small hole into a vacuum, that is called effusion. And then even though we say it's going into a vacuum, we often think of vacuums as like sucking, but really vacuums are just areas of very, very low pressure. And when those gases are going through the small hole, they are naturally going through the small hole. There's just less things pushing back at them because of the vacuum on the other side. And so they just happen to go through the hole. It's not like they're being sucked in, they're just not being pushed back out. They're just bumping and they just happen to go through the hole. And so the rates of diffusion and effusion are both related to that root mean squared average velocity. And so remember, we had our square root of the mean of the square, so that was the root mean square velocity. So they're both related to that term. And that means we can take the ratio of, we said that was also equal to the square root of 3RT over M. And so if we're taking that ratio, the 3, the R, and the T are going to be the same for both gases. And so that means that the rate is going to be inversely proportional to the square root of its molar mass, because we got our square root term in here. So here's some pictures to help you with the distinction between diffusion and effusion. For this diffusion picture, we see that we have one half the container is filled with hydrogen gas, and one half the container is filled with nitrogen gas. And then if we remove this barrier in between, the two gases will start to mix. And the hydrogen will be traveling faster because it's the lighter molar mass gas, and the nitrogen will move a little bit slower. But eventually, both gases mix. And so if we're talking about the rate of diffusion, we're talking about the rate in which these two gases mix. Effusion, we start with one half the container filled with gas molecules and the other part of the container having no gas molecules. This is just empty space. So when a vacuum, we talk about a vacuum, that just means lack of gas molecules. And so no pressure in there. And then we have a small hole form in this barrier. And now the gases, as they're bouncing around the container, if they happen to go through just the right way, they can pass through the hole into the other part of the container. And of course, the hydrogen here, it does have a lower molar mass, and so it is traveling much faster, which means it's going to be bumping into the sidewalls more often, and it might end up through the hole more often. And so you see here on the other side of the barrier, we have more hydrogen gas molecules, because they are lighter molar mass. So a scientist named Graham came up with a law of effusion, and that law is shown here with the rate of gas A divided by the rate of gas B is equal to the square root of the molar masses. And so rate is always defined as distance over time, and so that's what a rate is. And so I'm going to write rate is equal to distance over time. And so that's like its velocity, meters per second. And so we're going to, like, that's its velocity. We could put velocities here instead of rates, but rates are velocities in a way. And then, but rate can also be a generic way of saying like amount per unit time. And so rate here could also be, it doesn't have to be distances, it can also be amounts. So it could be amount over time. So that could be like moles per second. So there's a lot of different rates. So I have down here all these different options for this relationship. So we could have speeds, could be amounts of gas diffused, it could be distances traveled or times. All of that could be on this side of the equation. But rate is inversely proportional to its molar mass, and so if we have the rate of A, the denominator here will be the molar mass of A. The lighter the gas is, the faster its rate will be. So that's an inverse relationship. So here's another three-dimensional picture of a fusion happening. Let's do a practice problem related to a fusion. So here it says find the ratio for the effusion rate of hydrogen gas to that of krypton. And so since we had our equation as rate of A to rate of B, then that means this is going to be A to B. We're going to put this one on top because when it says this to that, we're really talking about A to B. So that's how it is set up. And so we've identified which gas is going to be labeled A and which gas is going to be labeled B. If it doesn't really specify, you can assign them either way. But if it's written like this, where you're trying to find a specific ratio in a specific direction, then you do need to infer from the words which gas needs to be assigned to be A. So that's going to be the molar mass of B, and that's going to be the molar mass of A. And so plugging that in, this is the ratio we're going to solve for. And so I'm just going to leave that as rate A divided by rate B. And that's going to be equal to the square root. And hydrogen is one of our diatomic elements. And so that's going to be, so that's, gotta remember that's H2. That's 2.016. And really these should be in kilograms per mole, but the kilograms part will cancel out. So you just gotta make sure that these units match. And I'll show you on the calculator that it's the same both ways. And then krypton is 83.80 grams per mole. So you can see here our units match, and so our units cancel out. So that will be the square root of 83.80 divided by 2.016. And so that tells us we'll have 6.4472 hydrogen molecules diffuse per every one krypton. Because, and 6.422 divided by 1 is a 1. So that's telling us our ratio is, we're going to 6 to 1, 6.4 to 1. As far as sig figs go, I had 4 sig figs in that molar mass. So I'm just going to round this to 4, and we'll just erase the 2. There we go. here's a practice problem for you. Go ahead and pause the video and try to work this out on your own. Unpause the video when you're ready to check your work. Okay, so this problem reads, if 0.5 moles of N2O effuse from an orifice in a certain amount of time, we're not told a specific time, so I'm just going to say that that's time t, how much N2 would effuse from the same orifice in the same amount of time? So we are looking for the amount of N2. So we're looking for, so remember that rate is, this case, it's going to be amount per time. And so the rate for N2O would be 0.500 moles per time. Before I get carried away with thinking about doing a calculation, I can think conceptually about how much my answer will be. So N2 is lighter than N2O because both contain two nitrogens, but this one also contains an oxygen. And so N2O is heavier, and this one is lighter molar mass. And since this is a lighter molar mass, more of it will effuse. I'm having issues writing with my tablet. So more is going to effuse from the N2. That means that I'm going to have an answer that's more than 0.5. And so therefore I can cross out the answers that don't make as much sense. So I need an answer that's going to be more than 0.5. That means if I end up with 0.399, I must have set up my calculation incorrectly. So let's think about this. So I'm going to have, I can assign either one to be gas A. And so I'm going to pick this one to be gas A. That way it's in the numerator when I set up my math. That's going to just make it a little bit simpler for me. And so my rate of A to my rate of B I'm going to assign that one to be B, is going to be equal to my square root, and this is going to be the molar mass of N2 over my, and then my numerator will be the molar mass of N2O. Let me go ahead and just write that that's going to be N2, and that's going to be N2O. So my rate of N2, it's going to be however many moles, I'm going to use N divided by T. And then my rate of N2O is going to be 0.500 moles per T. And these T's are going to actually cancel out because they appear in both the numerator and the denominator. They are the same amount of time. Now we have to figure out our molar masses. We have 14.007 times 2, and that's going to be 28.014 grams per mole. And then if I add on an oxygen, then that tells me my numerator is 44.013 grams per mole. So now I can use algebra and isolate this variable by multiplying both sides by 0.5. That's why I picked it to be in the numerator there, to make that simplification easier. So that tells me my n is going to be this. Let me go ahead and hit enter. And now I need the square root of 44.013 divided by 28.014. And then outside of that square root, I need to multiply it by 0.500. So that tells me my answer is 0.6267 mole. I need 3 sig figs, 1, 2, 3, and so my answer is 0.627 moles. Here's another practice problem for you. Go ahead and pause the video and think about this for a bit. Okay, let's go over this. It says a sample of argon gas escapes from a tiny hole in 60.2 seconds. Another unknown monatomic gas, X, requires 109.4 seconds. What is the identity of the unknown gas? So we are actually solving for the molar mass of the gas, and so the molar mass is here. So we have to solve for the molar mass of the other gas. So given our equation, I'm going to write our equation up here. Rate A over rate B is equal to the square root of, and then I'll have the molar mass of B and the molar mass of A. Now, I'm going to have to solve for one of these molar masses. So I have to think about algebraically which one would be easier to solve for. I think the molar mass of B would be a little bit easier to solve for because it's in the numerator. And so I'm going to assign this unknown gas to be B and argon to be A. So my rate of A. Rate is always amount per time. And so I don't know my amount, so I'm going to label my amount X and my time T. So it's the same amount of gas for both gases. So it's really this time that's going to be changing. So my rate is going to be whatever X is over 60.2 seconds. And then I'm going to have my rate, well, maybe I shouldn't have used X because it says here that the unknown is labeled X. So I'm going to label the amount. Let's see, what's a good variable? I'm just going to make the amount N for moles, however many moles that is. And then we're going to have the same amount of fuse for gas B in 109.4 seconds. Now, this is a fraction divided by a fraction, and so the ends will cancel out, but now we have these as 1 over that, and that's 1 over that. So when we do algebra on this, that really means that we have 101.4 seconds divided by 60.2 seconds. Rate and time are inversely proportional. And so even though the rates are set up with A over B, the times actually get set up with B over A. A car traveling faster will reach its destination in less time. This is going to be set up with the molar mass of A, argon, down in the denominator. So this is going to be my molar mass of argon. And that is 39.95 grams per mole. So I'm going to do algebra first and isolate my variable, and then I'll plug this into the calculator. So to undo the square root, I'm going to have to square both sides of the equation. I'm going to write in the square. Anything you do one side of the equation, you really need to do all over the place. So I'm just putting it, because I put equal signs in all of these, I really need to keep everything equal. And I do that by doing that operation all over the place. So it's going to be 101.4 divided by 60.2 squared is going to be equal to my molar mass of B divided by 39.95 grams per mole. And so now I can multiply both sides by 39.95. So now my molar mass of B will be equal to 39.95 times, open parentheses, fraction, 101.4 divided by 60.2, close parentheses, and then square the parentheses. So my molar mass is 113.3, which is not one of the options. Hold on. Okay, I found my problem, and it probably comes back to my stupid tablet not writing down my numbers or having a stupid delay. That's a 9. That's a 9 right there. I found my problem. So let's delete that and put in 9. Come on, write with me. 131. So that's 131.93 grams per mole. And so that is going to be matching xenon.